Hey, my name is Timothy, and I'm a part of the Middleton High School Robotics Club, more specifically, part of VEX Robotics. My presentation will mainly be focused on the more programming aspect of robotics, which is arguably one of the most important parts of it. For those that don't know, programming is basically creating instructions for a robot or computer so that it can perform a desired task. This is crucial towards robotics as a whole, as without the programming, a robot would just be a hunk of metal with some wires attached to it, which not very useful. So, a quick overview of what this presentation will be about. I'm really just going to go over some basic knowledge that you'll need to know in the world of programming, then a demonstration on autonomous code, and then a demonstration on Teleop code. Both of those will be explained further along. I should probably mention a few key vocabulary terms that may or may not turn up when programming. I'm sure that you've probably heard of these a decent amount of times, but hey, it's best for me to just go over it in case some people haven't. So firstly, there's velocity, which is simple yet crucial. Velocity is basically just the speed of which you're going. So I could say that a car would be moving at a velocity of 75 miles per hour down the highway, and that's a proper use for it. It's practically a placeholder for speed in this sense. Another key term is the brain, which the brain of a robot is basically just where all the programming and code actually runs, and where all of your wires are plugged into, which connects motors and sensors. Additionally, there's also the index. In programming, an index is where you write the code that assigns different ports of the robot to, or more specifically of the brain, to specific motors or sensors so that you can, actually run code. So if I were to assign a motor to, say, port 10, then whenever I instructed port 10 to do something in my code, then I would really be instructing that motor to do what I wrote. There's also the difference between a motor and a sensor, which is that a motor is a mechanism that creates an output, which is mainly just movement, while a sensor generates an input. So there's multiple different sensors, but one of the biggest ones is a gyrosensor, which a gyrosensor basically determines the positioning of your robot and where it is facing, so you can use that to run future code off of it to make precise programming. Another key thing are loops, they're basically just mechanisms of code which just condition the code, which basically that means that they check to make sure that a certain condition is met before it can run certain parts of code. So say you needed to move your robot so that it faced 90 degrees, right? And of course you could go ahead and put the specific measurements to move the motors, but sometimes they cannot be aligned correctly and it can mess things up. So if you want your robot to self-align, you could make a loop using a gyrosensor that said, hey, if I need to turn 90 degrees, check the gyrosensor and see what measurement it's at. If it's below 90 degrees, then turn right until it reaches 90. And then once it reaches 90, stop. If it's above 90 degrees, turn left until it reaches 90, then stop. So basically, it's just wherever you are, it adjusts, if that makes sense. I'll get more into the different types of loops later, but yeah. Finally, there are Teleop and autonomous. Teleop means that a program will run to make a robot controllable, meaning that you're really just programming a controller, while autonomous is just a program that runs a robot all by itself, meaning that no input other than the code is required to run the program. Teleop is used the most when it comes to robotics, as that's what you'll need to use in competitions to, compete. But autonomous is nearly as important, being used for their own dedicated brackets and competitions, as well as being used at the beginning of each match. Programming can be made through a few different ways, either through something such as writing it line by line, which is the way that most programming is done, especially in professional industries, or through some more block-like programming, where you can drag and drop commands and fill them in, which is less widely used but more user-friendly. This method is used on some more popular coding websites, such as Scratch, to make it more appealing and user-friendly to new coders, as to not force them away by somewhat confusing interfaces and languages of text coding. While the writing method is used in most, if not all, of the big programming languages such as C++ and JavaScript. Now here in VEX, we use the second method of code for our robot, but there is an alternative block-like coding tool made by VEX alongside with the text version to code with. Sadly, I won't be covering that as, like I said, we've only really used the text version to code, but it does follow the same basic programming rules, so it should be similar to text. It is important to note that the coding platform is always updating, so commands may be added, removed, or changed in the future, and that's why it's important to stay connected to the community to keep learning, which means you can go on YouTube, questions, or see other people's questions and just learn from there. There isn't much else to talk about programming, so it's time to go into it, actually writing down code.
The very first thing that you should always do when starting a program is index your motors and sensors, or whatever you have plugged into the brain of the robot. It's pretty obvious, but this is so important because if you don't have the ports of your motors indexed, then, well, your code really won't be able to run on your robot, as it never specifically tells the motors themselves to do anything. To index your motors, you write at the beginning of the program, underneath this section, the name you want for your motor or sensor, the type of mechanism it is, so whether it is a motor or sensor, and then the port or ports that are occupied by said mechanism. So, for example, you can see here that I want the motor on the left of a robot to be named LM for left motor, so I named it as such. Then I identified it as a motor, and finally I identified it as being in port 12. You do this to all mechanisms plugged into your robot, including controllers. Now that you have your motors and such indexed, you can start creating your programs. For the purpose of demonstration, I'll be creating one autonomous and one Teleop program, starting with an autonomous. For this program, let's say we'll make the robot move forwards 4 feet, turn 90 degrees right, and then move backwards 2 feet, all at a speed of 70%. Now, one big part of coding is adding comments to your code to say what certain lines are trying to do, for the purpose of when you need to go back to change something later, you can easily see where to change certain things. I'm going to go ahead and list out the different parts of code in said comments. So now that that's done, we can actually start the cool stuff. So here, for the move forwards 4 feet part, we can go ahead and start by setting the speed. If we set the speed after we start moving, then the speed won't change until, of course, after the movement, so we need to set it beforehand. Velocity can be set using the command motor.setVelocity, open parentheses, percent, comma, space, VEX, velocity units, degrees, and then close parentheses, semicolon. You can fill in the motor part with the name of the motor moving, so for this case it'll be LM since we're trying to do left motor, and percent with, well, the percentage of power, so 70%. It's also important to note that you can end every line of code with a semicolon to identify it as an actual piece of code that you need to run. So, since that line of code there will, of course, set the left motor's velocity to 70%, then we can keep moving along. If we just do the same thing to the right motor, then yeah, we're good to go. Now we come to actually moving the robot. There are generally 2 ways to go about this, which the first one is you can instruct the motors to have a specific amount of degrees, which is generally used for the purpose of accuracy, since, you can move a certain amount of degrees each time. And then there's the second option, setting your motors to move for a specific amount of time and then stopping them afterwards, which is generally harder to hone into specific movements, so for the purpose of this program, which we want more specific movements, I'm going to do the more specific route. The command for this movement is motor.rotate4, open parentheses, degrees, comma, space, VEX, rotation units, degrees, close parentheses, semicolon. Where motor is replaceable by the motor you are commanding, and where degrees is replaceable by the amount of degrees you are moving. It's kind of like the last one. We will fill in the motor with left motor, and to find degrees, well, we found out earlier in the year that 1 degree moves the robot about 0.034 inches, so 48 inches divided by 0.034 inches is about 1,412 degrees. But wait, there's one more thing. When running code, the program looks to run code from line to line in order from top to bottom, meaning that since we're making 2 lines of code to move both motors, they won't run at the same time. The one will run, then the next. In order to make them run together, you need to add a comma false in the parentheses after the rotation units. Remember though that you don't add a false to the last command in a list that need to run together, meaning that if I had 3 lines of code that I wanted to run at the same time, I would put a false at the end of only the first 2 commands. Now that we've added the false, our program will simultaneously execute this line as well as the next one of code. Then we just fill out the next line of code which is just the same exact thing except using right motor instead of left motor. The false part of the command only needs to be used when the robot is physically moving, since that's the only thing that needs, simultaneous coordination, as there's no other thing that really, moves two parts at the same time. Finally, there's one common practice that is executed right at the end of a string of movements, where you add a slight wait or delay in between commands. This is because you can give the robot some time to slow down and come to a complete stop before moving in a different way, causing no carryover movement. These waits are made using the command VEX : task : sleep, open parentheses milliseconds, close parentheses semicolon, where milliseconds of course is replaced by the amount of milliseconds you want to wait. And so here we're going to use a 50 millisecond wait. That's, a small amount of time for it to slow down, but it's still enough time. Now, if you wanted to do the second movement option, which is to time your motors, then you just need to make your motors start spinning, add a delay between that and the end, and then have the end be for them to stop spinning. You can make your motor spin using motor.spin, open parentheses, direction, close parentheses, semicolon, as well as, making them stop by using motor.stop, open close parentheses, semicolon. Motor is replaceable, obviously, by what motor you're trying to either start or stop, and direction can be filled in with forwards or reverse. Now the next step is turning right 90 degrees. For this step, like before, you can use exact commands that say just how much to turn, but for the purpose of demonstration, I'm going to be using a gyro sensor dictated as gyro in the index. To start off, you'll need to calibrate the gyro sensor using the command wait until gyro is calibrating, which basically just makes sure that the gyro can actually work properly, meaning that, when you turn 90 degrees, then it dictates that, hey, that's 90 degrees. Next, you set the direction that you're facing as 0 degrees, so that when you turn, your direct right is 90 degrees. This can be done with the command gyro.setHeading to 0, degrees, but the 0 can be replaced with whatever degree you really want it to be in front of you. Next, you just need to make sure that the robot starts spinning using the spin command on both your motors, where the left one moves forwards and the right one moves backwards, so that, it obviously spins to the right. Now, to make sure it stops spinning, you can make the command wait until the gyro hits above 90 degrees as its measurement, as the gyro isn't precise enough to always hit 90 degrees on the dot. This can be done using the command wait until gyro.heading, open close parentheses, is greater than 90. You could use wait until for other commands, as well as to make sure that the code doesn't run until something else happens. Once the gyro hits 90 degrees, just stop the motors with a simple motor.stop, and then you'll be fine and dandy, having turned full 90 degrees right. Now that we've turned, we're back to the simple part. For the last bit, all we have to do is just move backwards 2 feet. Do something similar to the first command, where you move 4 feet forwards, where you just use the rotate 4 command to move the motors for 706 degrees, which is just half of what you're doing. So since you only need to move half the amount, then half the amount of degrees is perfectly fine. But the only difference is that now you have to make sure that the degrees are negative, because you're going the opposite direction of what you were doing before. And once you do that, then that should be about it. You have a full program, moves the robot forwards 4 feet, turns 90 degrees right, and then backwards 2 feet. Now that I've finished the autonomous program, it's time to create the Teleup one. Teleup programs typically do have a bit less to write, but they are a bit harder because there are loops in them, which, of course, autonomous does have loops in more complex ones, but it's very common, or you need them in Teleup. Here we're just going to create a simple autonomous, one where the left analog stick of the controller controls the left motor, meaning you push it forwards, the left motor moves forwards, and if you push backwards, then the left motor moves backwards. And the right stick controls the right motor in a similar fashion. So, here is where you get a more in-depth look at loops. I may not have mentioned it earlier, but loops run the entire section of code they are associated with, even if the condition isn't met for the entire duration of the code. Meaning that you start it once the condition is met, but let's say you're halfway through and then you're no longer fulfilling that condition. Now go ahead and finish out the code. There are typically 4 types of loops: while loops, if-else loops, and else loops. While loops, as the name suggests, activate code whenever one condition is met, and are typically used to make sure that other loops are always running, making sure that, they're constantly checking for their required criteria. If loops are very similar, as they additionally check for certain criteria to be met before running their code, but they can be used with else if and else loops. Else if loops practically just allow multiple if loops to run at the same time, so that I could have multiple processes happening at the same time. Meaning that I could have an if statement asking for one button to be pressed, an else if statement asking for a different button to be pressed, and an else if statement saying that another button needs to be pressed. That way, any time that any button is pressed, then it'll run that certain section of code. Else loops just state what to do when no conditions are being met for the if or else if loops. Now it's time to start coding the Teleop program. Let's start with the left motor's movement. Putting a while loop at the beginning would be a good start to make sure that everything is always running. To make that loop, you write while open close parentheses 1, which is basically just saying that while 1 equals 1, which will always be true, meaning that the code's always running. Loops always begin and end with brackets, so I'm going to go ahead and add them starting on the next line for neatness' sake. Next, we begin an if loop to sense whether the left analog stick on a controller is being moved. Here, the left analog stick's vertical axis is identified as axis 3, and that's all the movement that we'll need for forwards and backwards, so that's all we're going to need to code. Here, we need to make a loop that identifies if the analog has been pushed either forwards or backwards. To do this, we can program said if loop of the while loop that says if controller position is greater than the dead zone, or if the controller position is less than the dead zone, practically. So let me break it down. The first half is saying that the stick needs to be at a position above the dead zone in order to activate the code, with the dead zone being the area that the stick can be in to still be considered the middle of the controller, where it doesn't matter if it's moving or not, it won't be detected. The two lines in the middle are just to say that either condition can be met to run the code, and the opposite side is basically saying the exact same thing as the first, but just if the position is less than the dead zone. So now that we have the conditioning statement made, we just have to make the movement statement. For this, we won't need to make a specific distance in the loop, as that would just make the movement too choppy and inaccurate, because if we do that, then it's basically going to say, hey, let's move forward, say 25 degrees, and then it's going to stop to repeat the progress, or to repeat the process again. So it's going to move 25 degrees forwards, and then stop abruptly, and then move 25 degrees forwards, then stop abruptly, and so on. And we don't really want that. So for here, we'll just merely spin the motors until the condition is not met, like when turning it with the gyro. To do this, we can use the spin command. But in order to make sure the speed adjusts to the controller's inputs, so if I push the stick halfway, then it only goes half speed, we can just make the speed of the spin stay with the same value of the input of the analog stick. You can do this because the analog stick creates an input ranging from negative 100 to 100 when going from the bottom to the top, with the middle being 0. Now, the specific command you can use to do this is shown here. Here it shows that the left motor will spin forwards at a speed of whatever position the analog stick is at, with the direction type bit just identifying which direction the motor will move, like mentioned before, and the percent units bit just saying that the PCT at the end means percent. That should make the left analog stick move the left motor whenever it does. That should be alright. Wrong. What happens if you let go of the stick? The motor would just keep moving on as if there's nothing to make it stop, since we only set it to spin. So that's where an else statement comes in. An else statement, like I said before, it shows the command that runs when no input is coming in. If you create an else statement where the if statement ended, and started and ended in brackets, then you can write to make the left motor stop using the motor stop command that we used earlier. Now all that you have to do is do all of that again in a separate while loop below this with another if and another else loop, and just change the motor to the right motor and the axis to axis 2, which is the right analog stick's vertical axis. And then there you go. That should be a fully operating Teleop program for you to move forwards and back with, using tank control, which is having the left stick control left side's movement, and the right stick control the left side's movement. Now, while it seems obvious, just remember that these commands are generally universal to all programs using this language, and you can change values and change the positioning to mess around with them and create more complex commands or just make them do different things than what's shown here. Well, that just about wraps up my programming presentation. I hope you enjoyed, and check out the other Middleton Robotics videos to learn more about the world of robotics.